Hello, in this video we will construct an experimental computer system that's able to calculate minus x or x to the power of y, and y is belonging to the natural numbers. The representation of positive and negative numbers in the decimal system by the use of binary system are shown here. The positive numbers are represented by using the least significant bits representing that number and leaving the most significant one equal to 0. But the negative numbers are represented in one of the two ways. Either by using the same maneuver for the positive numbers and putting the most significant bit equal to 1, or by complementing the similar positive number and converting each 0 to 1 and each 1 to 0, as this. In our experiment, we will use this method. The algorithm of our experiment is shown. First, z is equal to 1, e is equal to e, which is error, xo is equal to xo, yo is equal to yo. Then, there will be the input of x and y respectively. Then, x is equal to xo. Then, while y is not equal to 0 inversed, if x is not equal to 0, then there will be the output of z, else there will be the output of e. Then yo is equal to y. Then the computer system will test whether xo is negative or not. If xo is negative, then x is equal to x inverse, else as x will be equal to itself. Then the computer system will test whether y is not equal to 0 or not. If y is not equal to 0, then z is equal to z multiplied by x, and y is equal to y minus 1. And if y is not equal to 0 inverse, then the computer system will test whether xo is negative and yo is odd or not. If that statement is true, then z is equal to z inverse. Else, if it's false, then z is equal to z. After that, there will be the output of z. The data path that is required in our experimental system is this. It's basically composed from 4 to 1 multiplexer, 8 by n bits register file, n bits ALU, and a gate that will control the output. And finally, it requires a feedback loop that will return the value resulted from the ALU to the multiplexer to repeat the mathematical operation as many as needed. The control signals of our data path are shown. First, these two signals are to choose which port can pass its value through the multiplexer to the register file. This signal, which is WE, is to enable writing a value inside one of the 8 locations of the register file. WA012 are to choose a location from the 8 locations to write a value inside. RAE, RVE are to read a value through port A and B respectively. RAA012 are used to read a value through port A from one of the 8 locations, and that's similar to RVA012. But these three signals are to read that value through port B. The clock signal is required to change the status of the register file with each clock cycle. ALU0 and ALU1 are to choose a mathematical operation that can occur inside the ALU. And finally, OE is to enable the output through the gate. The conditions that will control our algorithm are tested through these 4 lines. First, y is not equal to 0 will be tested by putting an OR gate in the location that will save the value of y. And that's similar to x is not equal to 0. XO is negative will be tested by putting a buffer circuit in the location of the most significant bit of x. And when the most significant bit of x is 1, then y is negative, and vice versa. And finally, YO is odd by putting the same circuit in the location of the least significant bit of y, and when that bit is 1, then y is odd number. The next state diagram of our algorithm is this. It's composed from 13 different states. In the first state, z will be equal to 1, e is equal to e, yo is equal to yo, xo is equal to xo. In the second and third states, there will be the input of x and y respectively. In the fourth one, xo will be equal to x. After that step, the computer system will test whether y is not equal to 0 or not. If y is not equal to 0 inversed, then the system will test whether xo is not equal to 0 or not. If it's not equal to 0, then there will be the output of z. If it's inversed, then there will be the output of e. And e means error, because if both y and x are 0, then the result is error. If y is not equal to 0, then yo will be equal to y. After that step, the computer system will test whether xo is negative or not. If xo is negative, then x is equal to x inverse. If it's not negative, then z will be equal to z multiplied by x. And that step is the step that follows this step. After this step, y will be decremented by 1. Then the system will test whether y is not equal to 0 or not. If it's not equal to 0, then it will return to this step. If it's equal, then the computer system will go to a rest step where it will test whether xo is negative or not. If it's not negative, then the output of z will occur. But if it's negative, the system will go to another resting step. After that step, the computer system will test whether y is odd number or not. If y is odd number, then it will go to this step. If it's not odd number, then the output of z will occur. In this step, z is equal to z inverse. And after this step, the output of z will occur. And this step will return to themselves spontaneously without following any condition. This table shown is representing the next state table. The first, second, and third states will go to the next state without following any condition. The fourth state, here the computer system will test whether y is not equal to 0 or not. If y is not equal to 0, then it will go to the fifth state. If it's equal, then the computer system will test whether x is not equal to 0 or not. If it's, then it will go to the 12th one. If not, it will go to the 13th one. In the fifth state, the computer system will test whether xo is negative or not. If it's negative, then it will go to the 6th one. If it's not, it will go to the 7th one. The 6th one will go to the 7th one without following any condition, and that's similar to the 7th one, which will go to the 8th one. In the 8th state, the computer system will test again whether y is not equal to 0 or not. If y is not equal to 0, then it will return back to the 7th one. If it's equal, it will go to the 9th one without testing whether x is not equal to 0 or not. After the 9th state, the computer system will test whether XO is negative or not. If it's negative, then it will go to the 10th. If it's not negative, then it will go to the 12th. In the 10th state, or after the 10th state, the computer system will test whether Y is odd or not. If it's odd, then it will go to the 11th state. If it's not, then it will go to the 12th. The 11th state will go to the 12th state without following any condition. The 12th and 13th states will return back to their cells without following any condition. The remaining states will not go anywhere, and that's a brief explanation of the next state table. This table is showing the control signals of our data path with each state. In the state O, we will put the value of Z equal to 1, where we will choose O1 for the multiplexer and enable writing in the register file, and choose O location for putting the value of Z in that location. The other signals are don't care signals, and that means whatever the value of these signals, it will not affect our state. In the first state, there will be the input of X, where we will choose 1O by the multiplexer and enable writing to write the value of X in the location 1 in the register file. The other signals are don't care. In the second state, we will input the value of Y and save it in the second location of the register file. In the third state, we will enable reading of X through port A. Then we will pass it through the ALU and return it back and pass its value through the multiplexer by choosing 1-1 and enable writing to save it in the fourth location of the register file. After that, in the state 4, we will do the same thing with YO by enable reading of Y through port A and reading the location O10, pass it through the ALU, return it back through the multiplexer, and save it in the location 100. In the state 5, X will be read through port A by reading the location 001 and inverted by the ALU by choosing 10 of the ALU signals, return it back through the multiplexer, and save it in the location 001. In the state 6, we will read both port A and B respectively. Through port A, we will read the location 000, and through port B, the computer system will read the location 001. Multiply those two values by choosing 00 and return the result by choosing 11 of the multiplexer, enable writing, and save the result in the location 000. In state 7, the computer system will read the value through port A, and that value is from the location 010, which is the value of Y. Then the computer system will decrement that value by 1 and return the result by choosing 11 of the multiplexer, enable writing in the register file, and return it back to the same location. In the 8th and 9th states respectively, the signals are all don't care signals. In the 10th state, the computer system will enable reading through port A the location 000 and invert the value saved in that location by choosing 10 of the ALU and return it back through the multiplexer by choosing 11, then enable writing in the same location. In the last two states, there will be the output of Z and E respectively. In the state 11, there will be enabling of reading port A, and the value that the computer system will read is from the location 000, which is the value of Z. Then pass it without any change by choosing 11 from the register from the ALU and enable outputting that value. And in the 12th state, the same thing will happen, but with the value of E, which is saved in the location 110. The control unit of our data path is shown. This is the first part of the control unit, which represents the values of Q3 next and Q2 next. Q3 next is equal to 1 whenever Q3 or together with y is not equal to 0 inverse and Q1 and Q0. Q2 next is equal to Q2 and Q3 or Q1 bar or Q0 bar, or is equal to 1 whenever Q3 bar and with Q2 bar and Q1 and Q0 and x is not equal to 0 inverse, or y is not equal to 0 and together with the Q3 bar and the Q1 and the Q0 or Q2. Q1 next is equal to 1 whenever Q1 XORed with the Q0 or Q1 or Q0 and together with the Q3 or Q2 bar and y is not equal to 0 inverse and x is not equal to 0 or Q2 and y is not equal to 0, or Q3 and Q2 bar or Q3 bar and Q2 and Q1 inverse or Q0 inverse, and the whole is AND together with XO is negative inverse. Q0 next is equal to 1 whenever Q2 bar AND together with the Q0 bar or Q1 AND with the Q3 or Q0 bar or Q2 bar and the Q1 and y is not equal to 0 inverse and x is not equal to 0, or Q3 bar and the Q0 bar and XO is negative, or Q3 and y is odd inverse and together with Q2 bar or Q0. These are the control signals of our data path. Each control signal will be one in one of the following situations. S1 is equal to 1 whenever Q3 ORed with the Q2 or Q1 or Q0. SO is equal to 1 whenever Q3 is 1 ORed with the Q2 ORed with Q1 XNOR Q0. Write enable is equal to 1 whenever Q3 inversed ORed together with Q2 bar Q1 Q0 bar. WIA2 is equal to 1 whenever Q3 bar and the Q2 and the Q1 bar and the Q0 bar. WIA1 is equal to 1 whenever Q1 and together with the Q3 bar and the Q2 bar or QO. WIAO is equal to 1 whenever QO and together with Q2 bar or Q1 bar. RIA is equal to 1. RIA2 is equal to Q3 and the Q2. RIA1 is equal to Q2 and Q1 and QO or Q1 bar and QO bar. RIAO is equal to Q3 bar and Q2 bar or Q1 bar and QO. RBE is equal to RBAO and both are equal to 1. RBA2 is equal to RBA1 and both are equal to 0. ALE1 is equal to Q3 or Q2 bar or Q1. ALUO is equal to Q1 X NOR QO. Output enable is equal to 1 whenever Q3 and together with Q2 bar Q1 QO or Q2 and Q1 bar and QO bar. The control signal of our data path are shown. First, S1 is equal to Q3 or Q2 or Q1 or QO. SO is equal to Q1 X naught with the QO or together with the Q3 or Q2. WE is equal to Q2 bar and together with the Q1 and QO bar and the whole is all together with the Q3 bar. WAA2 is equal to Q3 bar, Q2, Q1 bar and QO bar. WAA1 is equal to Q3 bar and together with Q2 bar and the whole is ORed with QO and the whole is AND with Q1. WAO is equal to Q1 bar ORed together with Q2 bar and the whole is AND together with the QO. RIA2 is equal to Q3 and the Q2. RIA1 is equal to Q2 and the Q1 and the QO and the whole is all together with Q1 bar and the QO bar. RIAO is equal to Q3 bar and together with the Q2 bar and the whole is all together with Q1 bar and the QO. ALU1 is equal to Q3 or Q2 bar or Q1. ALUO is equal to Q1 X naught with the QO. Output enable is equal to Q2 and together with the Q1 bar and the QO bar or Q2 bar and together with the Q1 and the QO and the whole is and together with the Q3. RIE is equal to RBE and that's equal to RBAO and all are equal to 1. RBA2 is equal to RBA1 and all are equal to 0.